Hi everyone, welcome to the fifth lecture of the series on linear quadratic regulator. In this lecture, we discuss the discrete LQR and its derivation. Here is the overview. We start with the discrete LQR problem, then we move on to its derivation and the algorithm. In the discrete LQR problem, we consider the discrete time linear time varying system as given in equation number 1. If the system is time invariant, then AK is equal to A and BK is equal to B. The cost function is chosen as a quadratic sum of the states and control inputs as given in equation number 2, in which Qn is the terminal weighting matrix and Q and R are the weighting matrices for the state and control input. Now the discrete LQR problem is to find the control input UK at each time instant for the linear system, which minimizes the quadratic cost. Here n is the time horizon in discrete time, which is basically the number of time instants we compute or update the control input. Next we move on to the derivation of discrete LQR. Similar to the continuous LQR case, the major approaches used for solving the discrete LQR problem are the batch approach and the recursive approach. In the batch approach, the elements of the control input sequence are optimized together. So here we define a control input sequence U, which contains the control input from 0 till the end of the time horizon as its elements. And in the batch approach, we compute the optimal control input sequence U star by using some iterative optimization algorithms. Now in the recursive approach, the elements of the control input sequence are optimized recursively, which means one at a time. And the main example of the recursive approach is the dynamic programming. In this lecture, we will be following the dynamic programming approach for solving the discrete LQR problem. Here we consider the derivation for linear time invariant system as given in equation number 3, and the same derivation can be applied for time varying cases as well, with replacing A with AK and B with BK. Now similar to the continuous LQR, here also we use the cost to go function for computing the control input, and in the discrete time case, we define the cost to go function Vk as in equation number 4. Here Vk is the cost accumulated from the kth instant till the end of the time horizon. Now we have this important result which says that for linear system with the quadratic cost, the optimal control input will be a linear state feedback as given in equation number 5, in which Kk is the feedback gain. Moreover, the optimal cost to go function will be a quadratic function and can be represented as in equation number 6, in which Pk is known as the Riccati matrix. Now our task is to find an expression for the feedback gain Kk and the Riccati matrix Pk. So in this expression, we can replace this Vk plus 1 star with the xk plus 1 transpose Pk plus 1 xk plus 1, in which xk plus 1 can be replaced with the state equation. If we substitute this in the cost to go function, we obtain Vk star as in equation number 7. So here this term is basically the expansion of Vk plus 1 star. The optimal control input at time instant k will be the one that minimizes the cost to go function as given in equation number 8. Now, as per the first order condition for optimality, the optimal control input is obtained by equating the gradient of the cost to go function with respect to uk to 0, which results in equation number 9. So here we basically taken the gradient of this term with respect to uk to 0, and from this we solve for uk star, and that gives uk star as a linear state feedback, in which kk is the optimal feedback gain, and it is given us in equation number 10. Here we can observe that Vk is a quadratic function on uk. Now if we select R as positive definite, then Vk becomes a converse function on uk. Consequently, the first order condition gives a global optimal solution uk star. Also, if we select the matrix R as positive definite and the weighting matrices Q and Qn as positive semi-definite, then Pk plus 1 will be a positive semi-definite matrix, and the summation will be always positive definite, which ensures the inverse of this matrix exists always. Therefore, a unique feedback gain can be computed at each time instant. Here, in order to find the feedback gain Kk, we need to know the Riccati matrix Pk plus 1. Now, in order to find an expression for the Riccati matrix, we can substitute the optimal control input uk star in the equation for Vk star. So here we replace uk with minus kk times xk, and this gives Vk star as in equation number 11. Now this term can be simplified as in here. It gives Vk star as a quadratic function of xk. This term in green color, we replace it with pk, which gives pk as in equation number 12. And this equation is known as the difference regard equation or DRE. So we move on to the algorithm for discrete LQR, for which we require the system parameters and the weighting matrices. Then in the discrete LQR algorithm, we start with k equal to n minus 1 and go backwards in time until k equal to 0. Now using Pn, we compute the feedback in kn minus 1, and using Pn and kn minus 1, we compute Pn minus 1. And using Pn minus 1, then we compute kn minus 2, and this will be repeated until k equal to 0. For each k from n minus 1 to 0, we can compute the feedback gain using this equation, and the recording matrix using the difference regard equation. Now using the feedback gain at each time instant, we can compute the optimal control input at that instant. Here we can observe that if the length of the time horizon n is large, then computing and storing the feedback gains will be difficult. Therefore, in the case of LQR with a large time horizon and infinite horizon LQR problems, we can try to replace this time varying gain with a fixed gain, and this will be discussed in the next lecture. That completes this lecture. Thanks for listening.